All right, so we're on day 4. Our homework, you got all of page 2 in the packet and then another couple from page 1, 4A and 4B tonight. So you can pause the video right here to check your homework answers. And like usual on Wednesdays, I'll go to each of the worked out solutions and I will stay on there for 5 seconds or so in case you need to pause to look out at the worked out solutions. "32 was a challenge one. This is actually what we're going to work on today. This is called the washers method. So if you tried this one and had trouble, don't worry about it. Hopefully after today you'll be in good shape with how to do it. For 47, you wanted to take x squared plus y squared equals r squared and get y by itself and just work with one half of the circle. So like the top half of the circle would be positive square root of r squared minus x squared. That's your radius, so when you square it, you have r squared minus x squared. The antiderivative of r squared, because it's a constant, it's just r squared x. Then you got minus 1/3 x cubed. Fill in your r, fill in your negative r, and it works out to give you our volume of a sphere formula. All right, so day 4 is volumes by washers. So the first thing I want to show you is a little demonstration. Say we took this blue region here and we wanted to revolve it around y equals -2 there. So as we spin it around y equals -2, this is the three-dimensional solid that it would create. And to find the volume of that, what we would do is we slice perpendicularly to what we're rotating around, so we would slice vertically here. Each of our slices would have a little bit of thickness in the x direction. So that's our dx. And what we'd do is we'd add up all those different slices there, and they would represent the volume. So because we have a washer shape, okay, a washer meaning that there's a circle cut out of the middle, we're going to do an outer radius squared, pi times an outer radius squared minus pi times an inner radius squared, and then multiply that by our little bit of thickness, which is like the height of the cylinder. So if we go back and go to our day 4 in the notes packet. So if we've got a two-dimensional thing here, and I called, oops, purple's probably not the best color to use there, and I called that R1 and this R2, we would find the shaded space by doing pi times the bigger radius squared minus pi times the smaller radius squared. Well, why don't we carry that over to a volume? What if you had basically a cylinder with a middle chopped out? Let's call this H. So we would now, and we'll stick with that the outer radius is R1 and the inner radius is R2. So we would have pi times R1 squared times H minus pi times R2 squared times H. We could pull out the pi and the H, and notice that's just R1 squared minus R2 squared, where it's the outer radius squared minus the inner radius squared. Well, as I showed in the in the model a second ago, we're going to add up a whole bunch of slices of really thin washers. So the thickness will be close to nothing, and that thickness is essentially the height here, and that's going to become our dx in our integral. The pi we'll put out front, and then inside our integral, we'll just have this part. The radius squared for the outer minus the radius squared for the inner. So our first example on the bottom there, we've got x squared and square root of x. So those would both cross when x is equal to 0 and when x is equal to 1. So x squared looks something like that. The square root of x looks something like that. So we're looking for that space that's in between them, and we're going to spin it around the x-axis. So if we took one little slice of that region and spun it around, it would essentially look like that. We always slice perpendicular to what we're rotating around. So when we're slicing perpendicular to the x-axis, it is the x-axis that gets cut. That's why it tells us that this would be a dx in this case. We'll always have pi out front, and then it's just our outer radius squared minus our inner radius squared. So the function that we want for the outer radius is the one that is further away from what we're rotating around. So the one that's further away in this case is the square root of x. So we'll have square root of x squared minus x squared squared. And they were intersecting when x is equal to 0 and x is equal to 1. Now, if you weren't sure about the 0 and 1, because it's not always going to be as straightforward as this, you would just set those two functions equal to each other. We could square both sides and get x to the fourth equals x. Subtract the x over. Pull an x out. I'm going to move it up here. We'll get x equals 0. Add the 1 over. And when you take the cubed root, you get x equals 1. So just by setting those equal, we could get the values of x that are going to enclose the region. Well, from here, we're going to neaten up first. Square root of x squared is just x. This will be minus x to the fourth and dx. Keeping the pi out front, we'll do our antiderivative. 1/2 x squared minus 1/5 x to the fifth. And we're going to evaluate from 0 to 1. Stubbing 1 in is just our coefficients. Stubbing 0 in will give us 0 for both of those. So this is really 5/10 minus 2/10. So we'll have pi times 3/10, or in other words, 3 pi over 10. And what that represents is the volume when our enclosed region is spun around the x-axis, the volume of that three-dimensional shape that is created. Now that volume should always be positive, so if you ever get a negative answer, you know you did something wrong. All right, if we go to the next page, we've got x squared and 2x now. So x squared looks like that again. 2x has a y-intercept of 0 and goes through, has a positive slope, I should say. If you want to find where they're crossing, you can set them equal. We'll subtract the 2x over. You can pull an x out. set them each equal to 0, and you've got 0 and 2. So x equals 2 is the other spot that this is crossing. The y value where they're crossing, if you put 2 into either of them, you get 4. And we want to go over the y-axis this time. So as this spins around, an example of a slice will look something like that. So you always slice up your solid perpendicular to what you're rotating around whenever you do discs and washers. So we would be slicing perpendicular to the y-axis, so it is the y-axis that gets sliced. So because the y-axis gets sliced, this is going to be a dy. We'll have our pi out front. And because we've got that hole in the middle, that's why we know we're going to do our washer method. So we have the pi, and we'll do our radius squared for the outer minus radius squared for the inner. Because we're dy, though, we need to make sure we're in terms of y's. So our function that is further away from what we're rotating around is x squared. But we've got to take y equals x squared and get y by itself. So that would be x equals square root of y. So we'll have that squared to start out. And then our inner one will be the y equals 2x. We'll get x by itself in that one, and you'll get 1/2 y. Now be careful of your values on your integral. They need to be y values, and in our region, the y values went from 0 to 4. Always neaten it up before you take your antiderivative. So we'll have y minus 1/4 y squared dy. This will give us 1/2 y squared minus 1/12 y cubed. And we'll evaluate from 0 to 4. 4 squared times 1/2 will give us 8. 4 cubed is 64. 64 over 12. You can divide them both by 4, and you'll get 16/3. So we'll have minus 16/3. And then putting 0 in for both of them will give us 0. So this is 24/3 minus 16/3, which will give us 8/3. So we have 8 pi over 3. And our last one for the video, so we want the region in quadrant 1 that is bound by cos, sine, and x equals 0, and we're going to spin it around the x-axis. So x equals 0 is really just the y-axis. Sine looks something like that. Cos looks something like that. So the space we are looking for is this region right here. And we want to spin that around the x-axis. So because there's gap there between the region and the x-axis, that's why we know we'll do washers. Washers and discs, you're always slicing perpendicular to what you're rotating around, so it's our x-axis that gets sliced up. So that tells us we will be dx. We'll have our pi out here, and we're going to do some radius squared minus some radius squared. The first one will be the outer. So of those two graphs, the one that is further away from the x-axis is the cos graph. So I have cos x squared, and then the closer one is sine x squared. We start at 0, and sine and cos are first equal at 45 degrees, or in other words, pi over 4. So pi over 4 will be our top value. Now at this moment, we don't know how to do the antiderivative of cos squared or sine squared. We will learn how to do those eventually. So we want to recognize that's one of your identities that you saw last year. Cos squared x minus sine squared x is just your cos double angle formula. So we can switch this pi times integral 0 to pi over 4, and now it's just cos 2x dx. That's something we can do with a little u substitution. So u is 2x, du is 2 dx. We'll correct by a half. So put the 1/2 out front, and we'll have pi over 2. We're going to have cos of u in here now with a du. And fill our bounds in for x in our u equation to see what values of u we would get. So 2 times 0 is 0. Pi over 4 times 2 will give us pi over 2. Antiderivative of cos is just sine. And we're going from 0 to pi over 2. So we'll have pi over 2 times sine pi over 2 minus sine of 0, which that's just 1 minus 0. So we just get that that space is pi over 2, which is kind of crazy to think about. Pi over 2 is something we see a lot. That if you take that region, spin it around the x-axis, it's going to have a volume that is exactly pi over 2. All right, that's it for this video. So you got day 4 homework to work on. Have a great rest of your day.